All right, just a reminder, there are forward-looking statements in this presentation today. Please only make purchase decisions based on what is available in the product today. Welcome. So the title of our session today is How to Reduce System Noise Up to 98% Fast. And my name is Julia Nasser. I am a senior product manager, and today I will be joined by two of our data scientists, Irina Grabovich-Zoyev and Max Lee. So the goal of this session for our listeners today is that when you leave this session, you should be able to identify common sources of noise, map those problems to solutions in PagerDuty, and leave with some best practices for when you implement the features. And before going into depth into noise reduction, I want to spend just a couple of minutes going over what we mean by PagerDuty AIOps and how noise reduction fits into our suite of features. So the mission in AIOps is to help developers and engineers effortlessly discover and resolve issues to minimize downtime with the power of AI. And within the AIOps group, we are focused on solving a few key customer pain points. First, we see that our customers are drowning in noise. I don't think any of us want more data. We are dying from information overload. And what we've seen is that 69% of DevOps and ITOps teams from surveys have said they're struggling with an increased amount of data coming into their environment. And in addition to noise, once responders identify the real issue, then they are tasked with, how do I begin to make sense of this? So it's not surprising that 59% of responders in our survey said that finding the root cause has become harder due to the complexity of infrastructure and the pieces around it. And then finally, 47% say manual processes for P1 incidents are hampering productivity. It's a trade-off between innovation and firefighting. And to address each of these key pain points, we offer a full suite of features. First, we have a number of features to address noise, including suppression, dedupe, as well as alert grouping. For root cause, we have multiple features to provide our customers with contextual information to help our responders triage issues more efficiently. And then finally, we help remove toil via our custom webhooks and automation action solutions. So I wanted to provide that AOps overview, but today we're focusing on noise reduction. And in this slide, you can see how if you were to leverage all of our noise reduction capabilities, you could reduce noise up to 98%. So first we have deduplication. So this is for services with API integrations. If multiple incidents are triggering the same issue, your team can group these incidents using a dedupe key. Suppression, which is front of pipe rules to suppress no non-actionable events. Then we have service routing, which ensures that the events coming in are actionable and mapped to a service in PagerDuty, where each of those services represent a specific application or area of your system. And then finally, alert correlation. So this is where we use ML to group multiple alerts into an incident with a simple but powerful heuristics and machine learning. And this last area is where we'll focus today, which is our ML-based features aimed to reduce noise. We're focusing here because solutions such as suppression, deduplication are pretty well known and leveraged by our customers today. Where we do see customers missing out on additional noise reduction is in some of these ML features. And that's due to sometimes maybe our customers don't understand it well enough, or maybe they don't have the best practices implemented when they are using the feature. And I do want to point out that if you're interested in some of these other areas of noise reduction, we do have some links at the end of this presentation to help you. Also, if you're interested in event orchestration, there are some sessions on these topics as well here at Summit, so please check those out. So let's talk about our most recent ML-based noise reduction feature, what we call auto pause incident notifications. And with this feature, we apply machine learning to automatically detect and pause transient alerts that historically auto-resolve themselves. We do this so we can remove unnecessary noise from flapping alerts with a click of a button. And now I want to hand it over to Irina to explain how do we define a transient alert and how do our ML models detect these?
Thank you, Julia. That's a very good question. Indeed, the first phase in the development process was to define what is a transient alert. To define what transient alert is, we collaborated with our product and our customers. The main scenario we want to avoid was as follows. A responder receives a notification about an incident. While she is reviewing it, it's already auto-resolved by an integration. This situation is frustrating because it requires a context switch from the responder, not to mention that the notification could happen in the middle of the night. Learning from our conversations with customers and based on our experience in PagerDuty, in many cases the responder already knew that those type of incidents will auto-resolve. This information supported the assumption that historical data can be a good indicator to predict transient alerts. The next phase was to develop our prediction model and test it offline using our dataset and online after the EA launch. We ended up with two solutions, a prediction model and a real-time rolling count algorithm, and we decided to A/B test them in EA. We were aware that in some cases, our responders could make changes in their system that later trigger the API resolution. This is why it was very important for us to evaluate our model in EA using real customers' data. And we were glad to learn that our accuracy continues to be very high. In this phase, we also filed a patent that describes our novel use case and solutions. So let's go a bit deeper. The following workflow defines the high-level view of the prediction process for the chosen solution, the prediction model. The main input for our prediction model was the alert title, because our prediction happens on the critical path before the notification is sent. So we couldn't use additional information, such as the number of responders or time to acknowledgement and so on. Because when we would want to apply the model on a new alert, we won't have this information. The main logic we developed is in the alert title pre-processing module and, of course, the prediction model itself. In this workflow, you can see that the online pipeline, represented by white arrows, and describes a new alert that arrives to the system and a prediction model is being applied. For the offline daily retraining process, we use the yellow arrows. You can see that for both pipelines, the offline daily model retraining and the online to apply the prediction, we use the same pre-processing alert title normalization module. The received template is used as an input for a model prediction. One of the parameters that we tuned was a minimum threshold to predict that alert is transient. If the prediction score is higher than the threshold, we predict that the new alert we received is transient. We will pause the notification and give it a chance to resolve. Only in case it was not resolved, we will trigger a notification for our customers, similar to the scenario when the model predicted that the alert is non-transient. So let's follow an example of getting two new alerts to understand better the workflow. We will assume a minimum threshold of 0.8 and a user configuration of 4 minutes pause time. After the pre-processing phase, on both alert titles, you can see that each alert is represented by a template. We normalize the title by removing numbers, unique identifiers, URLs, etc. After applying the prediction model on the first template, which is in our example PD warning wildcard from wildcard, a score of 0.87 was received. It is higher than the 0.8, the minimum threshold we use in this example, so we will predict that this alert is transient. What will happen is that we will pause the notification for 4 minutes that our customer configured as pause time in this example, and the notification will be triggered only if it wasn't resolved during this time. For the second alert, which starts with PD error, our model output a much lower score as a prediction, 0.45, which is lower than the zero point 0.8 minimum threshold we chose for this example. So for the second alert, we will immediately trigger a notification for the relevant responder. Besides the prediction model that I just described, we also developed a real-time rolling count solution that used a similar pre-processing module for the title, but the prediction algorithm gave higher weight to recent behavior and used much shorter time period. The prediction model solution was more stable and it was retrained daily and used much longer time period for training. For both models, our EA evaluation showed above 90% precision in our predictions for both models. The prediction model solution outperformed the real-time rolling counts quite significantly. We saw that for 66% of the services, it had a higher accuracy. So the prediction model was a solution we chose when we launched the feature in GA. So why are we optimizing the precision metric and not, let's say, the recall? In this use case, we want to minimize cases for pausing non-transient alert, which can hurt our customers' trust in this feature. This is why we were maximizing and optimizing our precision. After launching the feature in GA, it was quickly adopted by many customers, overperforming the EA precision. We saw above 96% accuracy. This means that only 4% of alerts we predicted as transient and paused did not resolve and trigger the notification, when the noise from the remaining 96 was avoided. Of course, after GA, we continue to monitor our model accuracy. Now, I will hand it over to Julie and Max to talk about our intelligent alert grouping algorithm.
Thank you, Irina. So now we are shifting from a more recent feature, which was auto pause incident notifications, to one of our most popular noise reduction features today called intelligent alert grouping. So one of the largest sources of noise that we hear all of the time from customers is noise coming from duplicate or very similar alerts where responders are getting pinged over and over again for what is essentially the same issue. And with intelligent alert grouping, we use machine learning to identify similar alerts, and we also incorporate user behavior to improve those alert groupings over time. So this is where I will hand off to our data scientist, Max, to explain to us what does it mean to intelligently group alerts.
Thanks, Julia. Let's talk about how intelligent alert grouping, or IAG for short, works. In a nutshell, IAG works by comparing the text similarity between incoming alert summaries per service and will cluster together alerts that are most similar to each other in the same incident. Now, an additional grouping time window parameter at 5 minutes after the last alert determines whether or not an incoming alert is eligible to be grouped to an existing cluster. I actually want everyone to take a mental note of this grouping time window because we'll actually refer back to this later for a future product enhancement. Now, in addition to the text similarity, there's actually also a background learner that will adapt any user feedback due to errors and will adjust future grouping activity from what it has learned. So now that I have introduced how IAG works, let's talk about a few best practices that will make IAG work even better for you. IAG works by text similarity. So naturally, it works under the assumption that similar issues will have similar alert text. One of the things that can improve these groupings is to be more consistent when naming service, resources, and entities. For example, a resource named login database in one alert and login DB in another alert would potentially decrease the long-term accuracy of these groups. Another example where we can improve these groupings is to use human readable names for service resources and entities wherever that may be possible. IAG will still work with UUIDs, but may have a better long-term grouping accuracy using human readable names for these resources. Here's a hands-on example of how IAG works. Here you see a sequence of alerts. There are actually 3 unique alert templates here, namely permissions host fail, no data stale emails, and spunk alert 500. Now, normally you can expect IAG to group these alerts into 3 distinct incidents. However, because a user had previously indicated that no data stale emails is actually related to permissions host fail, the learners were able to remember this over time and group these 2 alerts together into the same incident. So all in all, given the above alerts, IAG was able to group them into 2 separate incidents. Let's now talk about an enhancement to IAG that we believe will make IAG work even better for more of our customers. So remember the globally fixed 5-minute grouping time window that I mentioned earlier? What if 2 alerts were further than 5 minutes apart? What if your service tends to have alerts that are 10 minutes, 15 minutes, but those alerts refer to the same issue? Wouldn't the service not have many grouped alerts and reduce IAG effectiveness? You were thinking that? You'd be correct, and we agree with you, which is why we have added a new enhancement to IAG called Flexible Time Window that will allow users to manually select this grouping time window per service. This is an example of how the future's UI might look like. But what if the user does not know what the best grouping time window would be, or just wants PagerDuty to handle it? Yes, we can do that too by helping you understand what the best time window should be and automatically recommend it to the user. To make sure this feature works as intended, we ran a simulation with the enhanced version of IAG on a service that typically has alert inter-arrival times of more than 5 minutes. In other words, the older version of IAG would likely not reduce much noise on this particular service. The slide shows the simulation results. The blue line represents the raw alert count through time. The red line represents the number of incidents created when using the older version of IAG without flexible time window, and the green line represents the number of incidents created with IAG using the recommended time window. As you can see, there were substantially less incidents created using the recommended time window, confirming that the new time window is indeed working. And now I will hand it back to Julia to wrap up this talk.
Thank you, Max, for going over that. Yeah, so everyone stay tuned for flexible time window. We're really excited about that upcoming feature as part of our AI Ops solution. And just a recap, we do have a full suite of AI Ops features that I covered earlier, including additional noise reduction features that you can leverage within event orchestration. And there are some other summit sessions on this topic, so please check that out. And finally, here are some resources to get you started on enabling the noise reduction solutions that we discussed today. Thank you for attending and have a great time at Summit.